So, good afternoon, everybody. Your Highness, ladies and gentlemen. So, welcome to uh, international online lecture with our colleague from Indian Institute of Geomagnetism. So, I'm Marzuki. It is my honor to be a moderator today. And the program this afternoon is as follows. So we will start with the remarks with our head of departments, and then we proceed to lecture and discussion. So in short while, we will start with the remarks by our head of departments. So may I invite Dr. Moldaris Nur to deliver a remarks. Dr. Moldaris Nur, time is yours.
Okay, thank you very much, Dr. Marzuki. Okay, good afternoon, ladies and gentlemen, speakers, lecturers, students, and guests. I'm very happy that we are all can gather here today to attend this online lecture. Thank you very much for Dr. Marzuki for arranging this event. Firstly, I would like to welcome Associate Professor Gopi Seemala from Indian Institute of Geomagnetism, India, to Microsoft team meeting of our department. We are really thankful and also grateful for your willingness to share your expertise to our students, academic staffs, researchers, and from guests from collaborating institute. For our attendees, especially our students, we hope that you can learn as much as possible about earthquakes and its signature in ionospheres. We are really looking forward to hear your lecture, and thank you. I give it back to Dr. Marzuki.
Okay, thank you very much, Dr. Moldaris Nur, our head of department. And well, I think we proceed to the main activity today. But before, I would like to introduce to you our guest lecturer today. He is Dr. Gopi. He is associate professor from Indian Institute of Geomagnetism. He graduated from, I think, Andhra University. Is it correct, Gopi-san?
Yes, Andhra University. Yeah, correct.
Okay. So he graduated from Andhra University in physics. If I'm not mistaken, because I just searched your curriculum vitae from internet, and I found that kind of information that you are graduate from physics. And some of his publication include space weather or space physics, I think also, and ionospheric physics. Okay, ladies and gentlemen, please give a warm welcome to our guest lecturer, Associate Professor Gopi Krishna Seemala. Time is yours, Dr. Gopi.
Thank you all. Thank you, Murdan Mr., the head of the department, and thank you, Marzuki-san, for
I think your voice is very, very small, Gopi.
very small now.
Yes.
Okay, this level is okay.
I don't know other audience, but for me it's still little bit slow. I mean
Maybe I'm
small.
using a headphone, so I'm maybe my voice is getting reduced.
But
No,
how is
Now you can hear me very well.
yes.
yeah.
Okay, this is fine.
Okay.
Yeah, that's
Now
great.
it's fine. Yes.
Yeah. Okay. Thank you, Marzuki, for inviting me for this lecture. And then I also thank the head of the department for giving me the opportunity. And I also thank you all the students to have the interest and in joining the lecture. Okay.
Actually, Gopi,
Huh.
Actually, some of audience come from Indonesian. I think Indonesian Aerospace Agency.
Okay.
Some of audience.
Okay.
Yeah.
That's great. I also welcome them. Okay. Let me share my screen. Share content. That screen. Yeah. Okay. Yeah. You can share. See the screen, right? Point. Yeah. Okay. Good afternoon, everyone. Today I'll be talking about earthquake signatures in ionosphere. Okay, so this is like see, we all know about the ground-based measurements like seismometer. We are very much familiar, and then I'll try to give an introduction about ionosphere for a couple of minutes, and then we'll start with how. And I'll start with how the signatures like are how the energy is transformed from the earth crust to the ionosphere level, and then how we will be able to see it in an ionosphere. Okay, so
Gopi, sorry, I don't see your slide, but I don't know whether other audience can see your slide or
Yes,
not.
I can see the slide.
you can see
Yeah,
the
you can
slides.
see it.
Yes, I can.
Make sure everybody has got the visibility of the slides.
Okay. So it seems that's not your problem. It's my connection problem maybe.
Oh.
Yeah, because Miss Mutia said that she can see your slide.
Then everybody could see. Everybody could see the slides.
Everybody could see the slide.
Yes, I can see
Yes.
your slide.
Okay. Okay. Please
Maybe
go ahead.
Matsuki-san,
It's okay.
you need to minimize that window or see where it is being shared in the your Microsoft Teams.
Okay, I think you can continue. It's okay.
Okay.
Yeah.
So before giving the introduction to the ionosphere and then how the signatures due to any seismic activity is seen in ionosphere, I would like to give a brief view of our institute for a few seconds, just to introduce our institute. So I come from Indian Institute of Geomagnetism. The primary objective of our institute is operational of magnetic observatories. So our institute operates 12 geomagnetic observatories that are indicated here in blue. So we have 3 regional centers and then 12 permanent observatories around the across means almost they cover the region of India. And then we have also our institute also operates 2 observatories in Antarctica, namely at the Indian research stations, namely Maitri and Bharati. So one of our oldest observatory is Colaba Alibaba Observatory. So we have geomagnetic observations starting from 1846 onwards, and then so there are we have continuous observations of more than 175 years of geomagnetic observations. So that is one good thing. Even in the World War I and II, a couple of observatories, oldest observatories, they had some break in data break, but we are proud to say that we do not have any data breaks. And in our institute, we, apart from the maintaining the observatories, geomagnetic observatories, we do research on space physics and particularly space weather, upper atmospheric observations, and then there are also people who also work on Earth interior, like studying the seismic activity of Earth, and then we also have a presence in polar research, where we see how the magnetosphere and then the geomagnetic storm interactions at the polar caps, and then how the ring currents, and then throughout the globe, everything. So we can say three major research. One is polar, and then the normal ionospheric research and space weather, and also at the ground level. So going back to the description of ionosphere. Ionosphere is a part of our atmosphere, which there is no specific strict boundary saying, okay, this layer starts from this region, but more or less we can say ionosphere starts at 50 to 60 kilometer altitude, 50 to 60 kilometer altitude during the day, and then at night it can go up to 100, means because of the recombination, we'll talk about it. And then the upper limit of the ionosphere, most of the time the significant upper limit of ionosphere, we keep it at 2000 kilometer, but then there is no fixed limit, but then it stretches still above, but then the region which is so high, and then where the ionized particles need not, they are not bound by gravity, but they are completely bound by magnetic field. There we call it as a magnetosphere. So practically saying, ionosphere is a part of the atmosphere where it is sufficiently ionized by the incoming solar radiation so that it can affect the radio signals or the satellite or any signal that is traveling through the ionosphere, any radio wave that is traveling through the ionosphere. If it gets affected, that gets affected, so that region we collectively call it as ionosphere. Even though at the surface of Earth we may see some ions and electrons, but then they are short-lived. But then the ions and electrons which are separated because of the incoming solar radiation at this region, they have a longer life, and then they sustain, and then these ions and electrons, they even sustain through the night till the next morning. So ionosphere, you need not worry, because we don't go much deeper into the ionosphere now. We just have some understanding what is the parameters of ionosphere. There are many parameters in ionosphere, but then we particularly concentrate on TEC. Means TEC is nothing but a total electron content. The total electron content is defined by 1 square meter cross section, say a cylinder or a tube, whatever we call, along the line of sight from the satellite to the receiver. So in that cross section, the number of electrons, the count of the number of electrons, what we call them collectively as TEC. So TEC is only one quantity, one single unit. It's a, we can say, a scalar quantity also, or even a vector quantity if we use the direction of the line of sight. So the TEC unit collectively describes what is the effect of the radio wave on the TEC, because whenever any radio wave is traveling through the ionosphere, so it is affected. It has a group delay effect as well as phase advance effect because of the changes in refractive index. So these changes, these group delay or a phase advance, is directly proportional to the TEC. So that way, and then ionosphere can be further divided into D layer, E layer, F1 layer, and F2 layer, where there is a change in increasing density, and then we see a cusp. There, D layer, the density peaks, and then there is a cusp, and then again E layer, there is a density increase. This is all dependent upon the number of species or number of the type of ions that are available in that region, depending upon that ion distribution we have. So we have those layers, ionospheric layers. We will not go much deep into it, so we'll directly skip on to, so this we already discussed. Okay, still I'll give, see, ionosphere, even though it has no limits, but then the TEC, where if we say the parameters of the ionosphere, they change day to day, obviously, because the ionosphere, the density is completely dependent upon the solar irradiance or the amount of ionizing radiation that is received from the sun, like X-rays and near and X-rays, soft X-rays, and even visible light is not affected. And then it has a diurnal variation for sure, and then there is a seasonal variation, and then there is the solar cycle variation. So solar cycle variation we'll skip for now because that will take some time. And then when we say ionosphere is ionized, again, say at the F layer means where the maximum density of the ionosphere, which peaks around 300 kilometers, because this maximum density of the ionosphere that is peaking, which we find because ionosphere is vertically stratified. At the F layer, the ion density or the electron density. The electron density is much more because we always speak in terms of electron density. The reason because that is what it is being counted, because the ions do not respond to the radio wave, and then when we count the radio wave, when we count the ionospheric TEC using the properties of how the property changes in the radio wave, they are referred to an electron, the number of electrons rather than the number of ions, but then more or less the same. So this electron density peaks around F region. Even at the maximum electron density at F region, only a fraction of ionosphere is ionized, say 0.1%, and after that the neutrals also decrease, and then still the ionization, the degree of ionization increases, but then this is much we described. So TEC becomes an important parameter in the ionosphere. There are many other parameters when we study the ionosphere, like the bottom side height of the region, and then the critical frequency of the layer, critical frequency of the layer. There are many parameters, but then this is the most measurable quantity, or because of the popularity of the GPS receiver or the GNSS receiver. So, and then the TEC can be derived very easily, and then this is and it is very continuous, and you can have a more coverage than using an ionosound or like other Doppler radars, but then the coverage is more using the TEC. So the TEC became popular, and then it also is a descriptive quantity of the ionosphere, because most of the time these days, whatever the satellite communication, say the frequencies of L band and S band, we are not very much worried about how the ionosphere is vertically stratified, rather than what is the net effect of ionosphere on the radio signal. So the net effect of the ionosphere on the radio signal is directly proportional to this parameter TEC, total electron content. The number of electrons the radio encounters this will affect the radio wave propagation, like the group delay or the phase advance. Okay, so TEC itself is a very descriptive quantity. Unless we want to see how the effects of other like ionospheric irregularities, then we need other parameters. Other than that, only TEC parameter is just enough for most of the studies. Okay. Getting back to the coupling mechanism. See, more people have observed, the researchers have observed like the signatures in ionosphere as early as 1960s, but they did not get them. They have a theory, but then they did not get materialistic evidences until recently, like 10-15 years ago. So whenever there is a volcanic eruption, or even a cyclone or a typhoon, or even an earthquake, of course is a major one. So this energy, there is a signature in the ionosphere. And how? Because the earth and atmosphere is a coupled system, the way we know, and then this energy exchange transfer takes place through many channels, like electromagnetic radiation, or radiative, thermal, and chemical or mechanical means. And then the lower atmospheric processes, so we will not be talking about, but then they are mostly meteorology. And then because when we say something is coupled in ionosphere, that energy coupling has to go through all these troposphere, stratosphere, mesosphere, and then to ionosphere. See, the energy that is being coupled through all these layers and then that reaches the ionosphere, that's where we see the signal. But then many people have a doubt, how come if the signatures are not felt very much here, and then how come the signature is clearly seen in the ionosphere? So we'll talk about that. See, whenever we say things about, say, apart from the gravity waves due to these due to this cyclone or the gravity waves that are affecting the ionosphere. When we say a volcanic eruption or even a nuclear detonation or even, and of course the earthquake, any seismic activity, the most of the time the energy is, the amount of energy coupled by mechanical means is the strongest. See, during an event of an earthquake, there are many waves that propagate because that originate because of a seismic activity. But then out of those, Rayleigh waves have the highest amplitude. And again, this amplitude, when we see in the like Z component, they are of the order of, say, micrometers, or even in a major earthquake up to a few centimeter level. And then this, because of this Rayleigh wave, this shaking, there will be a vertical shift or a vertical shaking. This vertical ground motion translates, has an effect on the vertical atmospheric column. And then this vertical atmospheric column also resonates, and I would not say resonate, also moves along with the ground motion. This produces the pressure of the order of millibar, which is very little, and it needs sophisticated instruments to measure how the atmospheric pressure is changing because of an earthquake. But then these pressure, because of these fast moving Rayleigh waves, they produce vertical waves in the atmosphere. These vertical waves, whose wavelength, so not the wavelength, the amplitude is very small, of the order of maybe a few millimeters to centimeter. These waves, they propagate upward with a constant kinetic energy, and then because of the energy conservation, as we go up, the density of the atmosphere reduces, and tenfold at the ionospheric height, and then accordingly the amplitude of these waves also increase that much, say again 10 to the power of 4 or 5 of that order. So these waves have become very big in amplitude at the ionospheric level. So not just at the ionosphere, not just the neutrals are moving because of these waves, or even the ions and electrons, they also move because of this ionospheric, because of these waves. So when we monitor, or when we get the measurement of this ionosphere, so there will be a significant changes in this, are a significant fluctuations in the electron density at the ionospheric heights. So that is much more easier to measure, because whatever the trans-ionospheric radio waves we measure, they are so sensitive to this the particular frequency spectrum, say 2 gigahertz or even 1.5 gigahertz, the L band, they are very sensitive to the changes in ionospheric density. Say particularly the GNSS frequency bandwidth, where what we generally use, L band, most of the GNSS like even GPS, Galileo, GLONASS, all of them use L band. L band means it consists of L1, L2, L5, L6, and even S band is recently being used in Indian navigation system, IRNSS. Still they are affected. So there we can easily measure, I would not say easily, but then I will show how they are impacted. We can measure these signatures. But then going back, so okay, this is what I am talking about. See how the density, we all know, this is only a pictorial representation of what I am talking. And then again, these waves, as I forgot to mention, they are the acoustic waves, or they travel at the speed of sound when they travel in the ionosphere. So this sound speed also increases, the acoustic speed also increases at the ionospheric height. It can go as close as 1 kilometer per second. And again, coming back to the ionosphere. So whenever we say of a signature in an ionosphere, there are many things affecting the ionosphere, not just the lithosphere. Lithosphere means any seismic activity, anything that is from the ground, we say lithospheric effects on ionosphere. But then there are many things, any irregularity from the bottom side or anything that is coming from the sun or like a solar wind or an interplanetary medium, and then if there is a geomagnetic storm that is affecting the ionosphere. So we see anything that affects the ionosphere, we have to separate it. Okay, so that separation becomes difficult. Okay, this is a pictorial depiction at what I am talking about. So whenever in an event of an earthquake, we have the acoustic waves, and then we have the Rayleigh waves, and this, as and when the Rayleigh wave is there, and then again, see these acoustic waves, what we assume, they are like a point source and then they go vertically up. Those have going vertically up has the most effect on the ionosphere. Those are slant can be negligible. And then again, as the Rayleigh wave progresses, at a Rayleigh wave velocity speeds, it can vary from 1 kilometer per second to 3 kilometer per second at the ground. And then again, every point will become a point source on the ground, and then they also propagate up. And then again, this will be acoustic speed, and then we see the signature. So in a way, we can see how the Rayleigh wave progressing on the ground, and that kind of spherical wave can be seen in the ionosphere. I will show you an case study also later on. So coming back to this, coming back to this point, yeah. So as I said, we have a variety of disturbances like space weather, volcanic eruptions, earthquakes, and then mechanical or chemical pathways, but mechanical is more effective. Chemical pathway is not so easy. Chemical pathways we discuss in a pre-seismic. Because when we say right now, whatever I am saying here, these are all co-seismic, because whatever the signature that is being seen in an ionosphere which is prominent is always co-seismic. Co-seismic means when the event is happening, and then it takes about 10 minutes from the epicenter to reach the ionospheric heights. The acoustic wave takes about 10 minutes approximately, depending upon the speed. So when we see a signature in the ionosphere, we are already 10 minutes delayed. So the event is already in progress. But this will be useful, say for example, in the prediction of a tsunami, or say for example, we do not have a seismometer, like 70% of our globe is covered with oceans. And then of course there are underground seismometers, but then you want to remotely observe the seismic signals or signatures in the ionosphere, then that will be useful. And for other reasons, I will talk in the coming slides. Again, in the case of a tsunami, of course, excuse me, this is that because of the gravity waves, these tsunami waves, whenever the tsunami progresses, these gravity waves, they go up, and then we see the signature in the ionosphere. And then even before the tsunami waves are felt at the coast, these waves once reach the ionosphere, they travel horizontally at the acoustic speeds, and then we will see much earlier in the GPS receiver about the incoming tsunami signature. So this is a possibility. Say for example, in a real-time monitoring of a tsunami, say for example, the tsunami, for example, the epicenter is far away from the coast, and then we have a sufficient time, say, because we need to take account of this 10-minute delay also. And then after that, the speed, this acoustic speed is much faster than the tsunami velocity of 200 to 300 meters per second, which is again at the surface level, both the acoustic velocities and the wave velocities, they are similar. But then as we go up, the acoustic velocity increases. At the ionospheric height, the acoustic speed is almost 1 kilometer per second, close to. So that way we can have an early tsunami warning system when we use a GPS receiver. Again, we'll discuss about what are the advantages and the disadvantages with this also. These are the observation conditions for the seismic signatures in ionosphere. These play a major role because of the following: the observational biases. Observational biases is what we call like how the receiver is positioned and then what time we are observing, like those things. Like say for example, yeah, again this is also covered here. Observational biases include many things like the characteristic of the receiver, the character, how the satellite is positioned, and anything how which is the type of receiver, everything will be coming in this observational biases. And the time of an earthquake, if an earthquake or a seismic event is at a noon time, then the signature in the ionosphere is amplified because the electron density is maximum during the noon of the day, and then in the night the electron density is still there in a flare. Yeah, we still see the signature, but then that will be a magnitude less. So the time of the earthquake also plays an important role, how the signature of earthquake is in the ionosphere. And then the solar flux. Again, solar flux is dependent on the solar activity, where most of you may be familiar. Solar has 11 years solar active cycle. So during the 11-year period, there is a minimum and a maximum. And during the minimum activity time, we have a less solar flux and then hence less ionization, and then obviously we have low TEC, low values of TEC. So during a high solar flux, we have high values of TEC, and then the signature will be much better. And then how closer we are to the equator. Again, the geomagnetic field of Earth also plays an important role in the earthquake signature. If the magnetic field lines are horizontal, then the amount of energy that is being coupled from the lithosphere to the ionosphere is more. As the geomagnetic field lines incline, this amount of energy coupled to the ionosphere will be little reduced. So obviously near the equator, where the geomagnetic equator is also there most of the time, so we have a more energy coupling. So if the receiver, the GPS receiver or a GNSS receiver is close to the equator, and then we have we are recording a seismic signature, we will be having much better signature near the equator than away from the equator. And again, satellite elevation and the geometry. Again, satellite geometry also plays a role, whether the satellite is in line with the how in which, because again, when we say the TEC is a measurable quantity in the direction of line of sight of the satellite. So if say for example we have an earthquake happening in the east and then we have a satellite in the east, we have a much better opportunity to record the signature much earlier. If it is in the west direction, the satellite is in the west, so we will be recording the same signature or with a little less magnitude, maybe in a latter part of the time. And then again, the nature of the earthquake. Also, it depends upon the thrust or its strike slip. And then because the signatures we see on an ionosphere, they respond very much to the vertical ground motion. So if the resultant earthquake produces a vertical ground motion, then the signature is much better. And then if it is a horizontal ground motion, we may not see ionospheric signature. And then the type of a lithosphere, sediments and the shield region. Yeah, this again is related to the propagation of the Rayleigh wave. We all know the Rayleigh wave doesn't propagate or propagates slowly in the sediments, and hence the signature will be very less in the sediment region, and the shield region the propagation will be faster, and then you see a better signature. So these are the conditions. And again, whenever we say the signature in the ionosphere, don't expect it to be as much better as a seismometer, because seismometer is records even the feeble earthquakes. But this in order to have a signature in an ionosphere, we need to have an earthquake of a magnitude 6 and above. If it is less than 6, it will be very difficult to monitor, because the changes in the ionosphere will be very less, and then they will fall in the noise region. Okay, and this is how the processes happen. There are the different processes how the energy from the lithosphere is coupled to the ionosphere. Say anything that is of a large scale on the ground, like a typhoon, cyclones, and even a volcanic eruption and an earthquake, they all propagate upwards. But then not just these. Say for example, we have a many gravity waves, like we have gravity waves throughout the day because of a topography, and then they also propagate. There are many things that will be affecting the ionosphere, but then those with a long wavelength, and then those with those which has a long preparation zone, are a long say what I meant to say, which has a coherent and a long wavelength. Those signatures can be seen much clearly rather than a small scale disturbances that are coupled to the ionosphere. See how they affect, like ionosphere is prone to the changes in the electric field, and then atmospheric gravity wave instability and ionospheric conductivity irregularities. Ionospheric irregularities is a different subject, but then still anything that can affect is all of these. But the coupling, what people perceive can happen in different combinations. Like atmosphere is also coupled. So whenever there are changes in atmospheric electric current, like a global electric circuit kind of, and then these changes can also propagate upward, and as well as the convective transport of charged aerosols, because these will be like in a precursory, because when we have a co-seismic environment, the ground motion plays a major role, and then these all things will not be seen, because these scenes will have a very little effect compared to the vertical ground motion. So these things, whatever are observable from the ionosphere. Okay, am I going too faster, or is it okay? Okay, we have time. So when we say there are many things that can affect ionosphere, but then the problem is isolating them. So we need to study multiple parameters. We need to study how the atmospheric electric current in a co-seismic environment, like a co-seismic study, we don't have to separate out this. But if it is like after post the earthquake or before the earthquake we want to study, we need many of these parameters to be studied, so that we can effectively isolate and then take away only the signatures of the earthquake. We'll discuss more in detail in where I will give a tabulation how everything changes. Say a simulation of how the ionospheric electron density undergoes changes. This is kind of a simulation, not necessarily the same. Say for example, the event of this is how the fluctuations of ionosphere are perceived. The color code is a density of the electron density at the ionospheric level. This is where the time, local time, and then this is the altitude. So following the earthquake, when we have a larger waves of the order of few hundred meters to few kilometers, then at the ionospheric height, these will change, these will perturb the ionosphere with that wavelength, and that those frequencies will be clearly seen, and then these changes will be sometimes vertical, and then the wave will be propagating horizontal. These waves, see, if we see in a TEC, so we don't see like at the absolute level we don't see much. But when we filter that wave, so we see that prominently, that signature. So for example, here, this is in response to a Chile earthquake. The earthquake occurred at this time, indicated by the red line. So we have a spectrum of the ionosphere filtered TEC. This is a TEC from the particular station TAMR of the day 2015 September 16 and PRN 24, means satellite number 24 of the GPS. So we can see the spectral content. We have a frequency around 4 millihertz peaking, because the 4 millihertz is 3.7 and 4 millihertz are the two particular frequencies, are the resonating frequencies in which the most amount of energy is coupled from the lithosphere to the ionosphere, or from the ground to the ionospheric level. So these resonating at these resonating frequencies, most of the energy is coupled to the ionosphere. So, and again, this most of the energy what we are talking is only about 0.01 or 0.02%, and then otherwise it will be very less at the rest of the frequencies. So when we look for a signature in a TSC, we usually look for a frequency around 4 millihertz, and then we see how the perturbations are at the 4 millihertz frequency region, and then this is a corresponding signature to this earthquake. There will be a delay of about approximately 10 minutes. Okay. So this is how a signature, but there is a problem. Likewise, whenever there is a disturbance from because of a space weather, or whenever there is a geomagnetic storm, or if there is an ionospheric irregularity, there also we see this kind of similar signatures, means not just at 4 millihertz. We see signatures at many other frequencies, depending upon the sampling of the TEC also. So there it will be very hard to distinguish whether this signature is because of an earthquake, or because of an irregularity, or because of a space weather event, anything. So because it will be very hard to distinguish, even though this frequency is very common. Say whenever you filter it, there will be 4 millihertz. Apart from the 4 millihertz, there will be other frequencies, but it does not necessarily warrant that, okay, there is only a 4 millihertz, there are no other frequencies, okay, then this could be an earthquake. No. So then what we do, we need to have a data from other GPS receivers, and then we plot travel time diagram, say like this, a Hodochrome. So then if they all fall in line, then this is because of an earthquake, and then we can even derive the Rayleigh wave and shock acoustic wave velocities, which have from this travel time diagram. I'll come back to this point again. Okay. Here, to give an idea of how the earthquake signature looks like, I took an event of this recent earthquake, Nepal earthquake of huge magnitude, 7.8. And then we took the data from these GPS receivers, which are indicated, they are color coded depending upon from which network of the GPS receivers, like a Nepal network, and then our own observatory IAG network, and then IGS network, and then IMD, and then ISGN. All these networks, we could have access to all these GPS receivers, and then we also wanted to see if there is any directionality, because earthquake rupture has a direction. Also, we wanted to see, because the rupture is in this direction. So we took the directions, we divided into zones, and then we wanted to see how the signature is because of the earthquake. So we have put the PRNs from the different receivers from the epicenter with the epicentral distance, and then we could clearly see the signature is very consistent through all the receivers. And then a couple of PRNs, we don't see much signature. The signature dies off very quickly. Like for example, if you go towards north, and then if we are towards south, this is towards the south direction, where we have a very clear-cut signature. And then here, this panel, gives zone wise, like zone 1, like southeast, this zone where the earthquake rupture is in this direction. So this is that zone. We could see a very clear signature because the propagation of Rayleigh wave, and also it could be due to the topography because we have a Tibetan plateau and then the Himalayas. Of course, the signatures are there always, but then the significant signatures are in this direction, in this zone, and then we derived the velocities from this travel time diagram, or simply put, we can call even hodochrons. The velocities of Rayleigh wave and shock acoustic waves from the TEC, and then we matched. Okay, this is again for better clarity. So we got the velocities of approximately 1180 meters per second for the shock acoustic wave, and then 2.4 kilometer per second for the Rayleigh wave from this travel time diagram. But then also we tried to see how the spectrum changes from closer from the epicenter towards the Andaman arc, means towards the southeast. See these two modes, SAW waves and Rayleigh waves, shock acoustic waves and Rayleigh waves. They are together when they are closer to the epicenter, quite naturally, because they did not disperse much. But then as you go away from the epicenter, we can even clearly see two different signature. The slow mode and fast modes, they are separated out because of course they travel with different velocities. And this is also a simulation that was carried out by a couple of researchers, like how the earthquake obtains that shape. Like say at 100 kilometer, this is pretty much closer with the ground, means of course closer with the ground vibration, and then as it goes up, they compress and then they come out with this shape, inversed N shape, what we call, because of a couple of frequencies. When as they move up, only couple of frequencies will be able to pass through the ionosphere, but then at each layer, couple of frequencies, they dissipate their power, and then the frequencies they go like the fast mode and the slow mode, they converge together, and then we see a simple this shape. This is a typical ionospheric signature in response to an earthquake, which is more or less seen. This is a simulation done by Chum et al. And then coming back to the Nepal earthquake, what we did was we wanted to see how consistent is the Rayleigh wave velocity that is derived from the ionospheric TEC alone with the seismic. See, the color-coded contour map is from a seismometer, from an Acton et al. Paper, so publication. So these color codes indicate how the velocity of the Rayleigh wave was in this region, India and the surrounding regions. So, and then the numbers which were given on numbers superimposed on the top of this color coded contour map is derived from the TEC. So the TEC velocities means when we say here at the IPP, ionospheric pairs point, at the ionospheric altitude, when we measure a Rayleigh wave velocity, we attribute to that particular point. Where say for example a receiver is here and the satellite is here looking in this direction, and then at a 350 kilometer height, the line of sight intercepts this point, this particular latitude longitude. This particular latitude longitude does not belong to the receiver, but rather the intercepting point in the ionosphere height. At that height, we measure the velocity of the Rayleigh wave from the signature, ionospheric signature, means two corresponding signatures, so with a time delay, and then we see how much is the time difference between two signatures, and then calculate with the time, simple dt by dt, then we get the velocity, and then that velocities are plotted. So we can see more or less these velocities that are obtained from the TEC, they are in agreement with the velocities, Rayleigh wave velocities obtained from the seismometer. So this proves that the seismic signatures are obtained. They just follow the ground motion, not because at the ionospheric heights the acoustic wave velocity does not change much. But as I said earlier in the earlier slide, say for example we have an earthquake in Nepal, and then the Rayleigh wave progresses in this direction radially, and then when we take, depending upon the region, the Rayleigh wave velocity, depending upon the crystal structure, the Rayleigh wave velocity changes depending upon the crystal structure. And then at each point, at each point on the crust, this Rayleigh wave also acts as a secondary source, and from there the acoustic waves emanate and then they go to the ionosphere. So at every point the Rayleigh wave acts as a source. So obviously whatever the signature we see in the ionosphere is not from the epicenter. It is from the Rayleigh wave progressing in the Earth's crust or at the surface of the Earth. So that surface wave motion is transposed in the ionosphere, and then so we get the same velocity at the ground level. Whatever the Rayleigh wave velocity has at the ground, that same velocity is seen in the ionospheric level. Okay, that is what we means. This is being there theoretically, but we could see in this particular event. And then coming back to till now we have talked about earthquake co-seismic signatures, but then let us talk about the most interesting topic, the precursors, because this is what we are very much interested. If there is a possibility to predict the earthquake, then everybody will be very much interested. So there are many studies, not just from the ionosphere. There is like radon, flux, or the ion flux. People have done studies like they say we could see some kind of a signature 2 months to couple of months to 2 weeks in advance, and then outgoing long wave radiation, people even say again 2 weeks. This is all depending upon how the preparatory zone is preparing, and then again the changes in the air temperature, and then the changes in the air relative humidity, and even the ionospheric variations. So people have been saying even couple of days or even 1 week before they could see an anomaly in the ionosphere. Yes, but then the problem is identifying the anomaly. See, there are many things could happen theoretically, but then there is a lot of noise out there in the atmosphere because of many things, and then whatever the signature or the anomaly we want to see is buried very much in the noise. So one can take up a study involving all these parameters and then compile them all together in real time, and then hopefully someday we have a precursor, because most of the studies that were done is after an earthquake. Like whenever we say there is a precursor, where we have an earthquake, and then after an earthquake, okay, we go back and study all the data sets, and then say this is a precursor, but then that is a kind of a post-mortem, not really a precursor, right? Say again, coming back to the same pictorial depiction. See, many of the things there are many things that relate to the ionosphere. When people say there is a signature we see in an ionosphere, say for example, this is a ionosphere. Say when there are many things like when the microfracturing occurs, there is at the surface level there are a production of ions, and then radons, and through which we have an ions, and then that changes the electric field depending upon the preparatory zone. That changes the electric field of the lower atmosphere, and then that change in the electric field will be propagated upwards in an ionosphere. Say for example, a 0.4 couple of volts in the order of an electric field change in an order of volt will produce a change of a 0.1 means 1/10 of a volt, decivolt at a rough layer, but then that is enough to perturb the ionosphere, because the advantage of ionosphere is any small signal is amplified so much. That is an advantage as well as a disadvantage, because that kind of a change can be produced by a regular atmospheric ground wave, and then any lightning activity, any, and even the topography itself keeps on giving those signals. So ionosphere is amplifying many of those signals. The only problem is finding which signal is which. That's where we stop. Like, I wanted to study, but then this will, but still we can say for example, I don't want to offend any, but then even this is one of our colleague, my colleague, she did also this kind of a study, seeing how the anomaly in an ionosphere is. She took say for example, she wanted to see, okay, there is a storm, and then what she does, I'll just explain. There she tried to segregate, like last 15 days, how the ionosphere is changing. Or she wanted to take a trend of how consider the changes in the ionosphere are a mean diurnal change for the last 15 days, and then she wanted to decide how the ionosphere changes are today, whether they fall in the upper quartile or in the lower quartile. And then they wanted to see how many times the ionosphere has been in a day. Say for example, this is the earthquake day when you focus on here, and then they wanted to count anomalous counts, how anomaly, if there is a positive anomaly, or if it is a negative, if there is an enhancement, it means a positive anomaly, there is an increase in the ionospheric density. If the ionosphere is decreasing, then it will be a negative anomaly or a depletion. So they wanted to see how many times the ionosphere is increasing, and then how many times the ionosphere is decreasing. So they claim, means many people claim that, okay, this is the earthquake day, and then we see lot of enhancements from multiple stations. They choose couple of stations in this region for that earthquake, and then they found enhancements here, and then say this could be a precursor. Okay, but then yes, there are many studies regarding the precursors, and we are progressing. I would say we are progressing definitely in a direction where sometime in future we could be able to predict, but we'll hope for the best. Now, any questions? I feel free to ask any doubt in between, because maybe I was a little bit faster. But then if anyone has a question, we can go back to the slide. We can have a discussion, because we have half an hour more to discuss, right?
Yes. Okay. Okay. Can you hear me, Gopi?
Yes, I can hear you.
Okay. Because we have heavy rain now here, so
Oh.
so yeah, I'm not sure that you can hear me well.
Yeah, I can hear you well.
Okay.
Yeah.
But anyway, thank you very much for very interesting talk. Yeah, because for me, because my field is lower atmosphere, so
Yes, yes, yes.
this your presentation is really interesting for me. But I think all the audience say the same thing. Okay, so now if anyone has any questions, I'm sure Dr. Gopi would be pleased to answer them.
Sure,
So
sure.
please, I think if you have some question, please raise your hand. I think we have some icon in the Microsoft team, raising hand icon. Okay, okay. We have one question from Miss Mutia. Miss Mutia is our faculty member.
Okay.
And she is studying about the lower atmosphere.
Yeah.
Okay, please, Bu Mutia.
Okay, thank you, Bapak Marzuki. Hello, Dr. Gopi.
Hello, madam.
Thank you very much for your nice presentation. That's maybe new knowledge for us. And I want to know about your research. You study about how GPS signal, and you can know about the total electron content. And now, could you explain from your research, how do we know or estimate that plasma depletions after or when earthquake or tsunami occurs? Maybe that's a simple question.
Okay.
And you can.
See,
Thank you very much.
yeah. See,
Okay.
when they say plasma depletion here in the last slide, which I have shown, they meant to say not the actual plasma depletion at the time of an ionospheric irregularities. Rather, they want to mean the reduction in the TEC compared to the previous day or a following day.
Oh,
See,
okay.
that's not an actual plasma depletion. Plasma depletion is when we say for example, now there is a plasma when a satellite is moving through, and then you encounter a reduction in the TEC for that particular time, and after that again the TEC recovers from that time within like 15 minutes or half an hour.
Okay.
That usually happens after post sunset, like after sunset time, where we have a generation of ionospheric irregularities. There we have a plasma depletion. But then this plasma depletion, what the people mention in the paper, they say this depletion is means a reduction in the TEC for a 6-hour duration.
Okay.
And they count if a TEC is reduced for continuously 6 hours compared to a previous day, then they say it's the reduction in the TEC, plasma depletion. But then usually plasma depletion is not a right term for that. You can say that plasma, or you can say TEC decrease, because
Yeah.
entire day the TEC is decreased, not just at one place, right? When you say
Right.
plasma depletion, at one place there is a decrease in TEC, and other places the TEC is same. That is different. When you say the TEC is decreased throughout the day, then you cannot say a depletion.
Okay.
So people has done a couple of studies like that.
Okay. And then you said that you estimate this using GPS dual frequency
Yes.
to measure that CAC. Could you explain a little bit about it?
Sure. See, there are many, whenever a radio wave propagates to the ionosphere, there are many things the radio wave experience. There is a delay. Obviously, there is a delay even because of a troposphere and water vapor and everything. But then when we have two frequencies that are received from a satellite, say ionosphere is a dispersive medium. Dispersive medium in the sense ionosphere affects each frequency differently. It's not the same for all the frequencies. When we have two frequencies, one frequency will experience a delay and maybe little or more compared to a second frequency. The experiences, ionospheric effects on the frequencies, they decrease with increasing the frequency. Say if the frequency is increased, then the delay is reduced. Right, vice versa. So if you have two frequencies, and then we assume that two frequencies are simultaneously transmitted at the satellite, but when we receive them at the receiver, one will arrive faster, one will arrive little slow. So when we measure this time delay between these two frequencies, that delay is proportional to the TEC of the ionosphere.
Okay.
Because otherwise, in a lower atmosphere, when we assume the two waves are two frequencies are traveling, they will be equally affected by the troposphere. So there is no differential motion there. So they will be changed only in the ionosphere. Because of this dispersive nature of ionosphere, we can easily derive TEC. But we need two frequencies.
Yeah. Okay.
At least.
Thank you very much. Very nice explanation.
Yeah.
Okay,
Thank you so much.
Yeah, it's a great question and good answer. Okay, next, please. If anyone has any questions, please raise your hand and Okay, so we have one question from Anissa.
Okay, sure.
Okay,
Yes,
please.
Mr. Marzuki.
Anissa. Okay, please introduce shortly about yourself first.
Hello, Professor Gopi Seemala.
Yes.
Nice to see you. Before I want to say thank you for the great presentation. Let me introduce myself first. My name is Anissa Fahmina. I'm a third-year student in Department of Physics in Universitas Andalas. I want to asking a question, Prof.
Sure, sure. Please, please.
Okay, I want to asking about how accurate is the earthquake prediction based on the TOC perturbation measurement?
See, as of now, we would say it is very difficult to predict earthquake using TEC alone, because many people have been doing this TEC prediction. Yeah, then if we are doing, I would say the TEC is available throughout the globe, right? And then we have at least one earthquake coming every month, which can be easily seen in the ionosphere, because to be seen in an ionosphere we need an earthquake of magnitude at least 5 or 6, a minimum magnitude of 6. Sometimes 5 is also visible, right? That kind of earthquake is easily happening around the globe, around the world, at least once a month, right? So we should have predicted by now, but we are not able to predict, because the reason is when we see a signature in the ionosphere, that can be because of many things. We can only confirm if we are clear to say, okay, this signature is not because of a space weather event, this signature is not because of some gravity wave, this signature is not because of some typhoon or some many things could any geomagnetic disturbances in the earth, like because of a geomagnetic storm there will be signatures. And if we are able to eliminate everything, then we can clearly say, okay, this is because of an earthquake. For that, one has to do a real-time data, and then but most of the time we could see many people are using offline data. It's not real-time data, offline processing. If one is doing a real-time processing and then they combine with many stations, say for example you see TEC from many receivers and in real time, and then you have to rule out why if a TEC is increasing at a particular location, say for example in a 200 kilometer or a 300 kilometer radius, because a minimum of 200 kilometer preparatory zone is required so that it can affect the ionosphere. If something is less than a 200 kilometer zone, then we cannot say that it will affect the ionosphere. Okay, so at least a 200 kilometer zone coverage we need, and then if we can say simultaneously see a signal in many receivers, and then we can say there is no space weather event, there is no geomagnetic storm, there is no other thing, then we may be able to say it could be due to an earthquake. But then again, people, whatever so far the studies that happened till now, sometimes the people say they have seen a signature 10 days before, they have seen a signature 5 days before, they have seen a signature 3 days before. There is no consistency. There is, again, there need to be a plausible mechanism also. When you say you see a signature, you need to explain how, like what is the physics behind it. See, the physics, as per the physics, people say whenever there is an electric field build up in a 200 kilometer preparatory zone because of the earthquake microfracturing, so there will be a release of radon gas. Means that's still a hypothesis, not proven. And then this gas will give rise to increase of ion counts at the surface level, and then change in this will also change the electric field at a lower atmosphere, and then this change in the electric field will be propagated to the ionosphere, and that will change the density of ionosphere. So that is what we are talking. But every day the density of ionosphere changes, say by a magnitude. Say in the night, if the TEC of ionosphere is 5 to 10 TEC units, in the day it will be 40 TEC units. So, and again, the next day it is not necessarily the same, because the next day the density will be again changing. It's not like yesterday it was 40, this day it may be 50, because due to a meridional wind or a zonal wind, we do not know. We need to also see the same. The difficult thing is, at the ionospheric heights, we do not have a measure of winds. At a lower atmosphere, even up to 60 kilometers, we can have a radar to measure the wind velocities. But at ionospheric heights, we do not have a measure of winds as of now exactly. So many things put together, and right now we could say it is not so possible with a TEC. Okay.
Okay,
You could
thank you,
understand?
Prof.
Yeah.
Yes, I will
Okay.
understand. Thank you for the great answer.
Okay.
But one
Thank
can
you.
use multiple techniques like radon and then electric field measurements and then atmospheric other parameters, and then if they see an anomaly in all of these parameters, then one can say there could be an earthquake coming up. That could be a possibility.
Okay. Okay. Thank you, Anissa. Okay. So it's very interesting because, like a signature in the ionosphere that come from many waves.
Yeah.
So we need to mix many sources to predict this earthquake as well.
Yes, yes.
Okay. Okay. Please, if you have some question, so we still have time. I think we still have time about 10 minutes. Okay, now we have one question from Mr. Aprizal. Mr. Aprizal is from the Indonesian agency, aerospace agency,
Okay.
Dr. Gopi, and he is one of expert in these topics actually.
Okay.
And I'm sure he would like to ask some interesting
Sure,
questions.
please.
Okay, please, Mr. Aprizal, please turn on your microphone. Hello.
The microphone is muted. You can unmute it.
Yeah. Hello. Please turn on your microphone first. Now it's tuning off.
Maybe Mr. Afrizal have some trouble, and Bapak Marzuki maybe can help to.
Or you could also send your question in the chat room if you have some difficulty to.
Yeah, sure. You can write it down.
Yeah.
Please.
Hello. Okay, I think we wait, but if some other have some question, please raise your hand. I think there are some students here, and some of them have a little bit basic about atmosphere, at least the lower atmosphere. But some of students have basic about the upper atmosphere because they are doing some final projects for their thesis in this topic.
Yeah.
I think if you ask some questions, so you will get a good score from Miss Mutia, right?
Yes, right. I'm waiting for student.
Yeah. I think you have a special contract with them.
What do you think about using Ionosphere data for earthquake prediction? Is it possible?
Okay.
Yeah. See, Ionosphere has this. People have been using Ionosphere data in a continuous mode. Like say, there will be say nowadays there are ionospheres which can give ionogram every even 2 minutes. Some people even run it at a continuous mode, like every 2 seconds at particular single frequency, or like a couple of frequencies, say a frequency in a corresponding to a F region or an E region. People are doing that, but even still, it will be the same thing. Like there are the changes what we see in an ionosphere data. There are many changes day to day because of many things that affect it. But then unless we know there is an earthquake, we are not able to attribute that change to an earthquake. That we are doing after an earthquake, but we are not, unfortunately, we are not able to do it before an earthquake. Because if you want to do it before an earthquake, you need to know, you need supporting evidence, like okay, it is not because of any other mechanism, like any other irregularity. It is not because of any irregularity in the solar wind. Say for example, whatever we have a constant stream of charged particles that are bombarding our earth from in space. They are if they change their density, that will affect the magnetosphere, and then they change the ionospheric current system, and then that will change the density in the ionosphere. So there are many things. If you take a look at the ionosphere data day to day, you can see what is the variance in the ionosphere data. The variance in the ionosphere data is so much when you compare it to the earthquake signature, that is well below the variance level of the ionosphere data. So if there, it's not like it's, yeah, it is recognizable, but then when we know, okay, this belongs to the earthquake, because when we compare it with a couple of other simultaneous measurements, then only we could say. Yeah, the people have done saying that, okay, we have seen a signature in an ionosphere, but then only after the earthquake, not before an earthquake, as of now. Because we don't have a supporting evidence to say, oh, okay, this is because to this. And then even if a signature comes, they do not know which direction where the earthquake was. Because that is also a thing. You cannot say, roughly say, oh, the earthquake can happen anywhere in 1,000-kilometer radius or 500-kilometer radius. Then you will be putting all the people in panic. Right? So we need some measurements, simultaneous measurements also on the ground, because like radon, you have to, radon reacts to, okay, yeah, radon reacts to the day-to-day changes in the temperature, radon reacts to the relative humidity. So you have to take off. Even now, people are not able to smooth out radon, like they have to take out day-to-day variability, and then they see what is the anomaly in the radon. Then that will be a good precursor. Means, at least from the studies, we could see the radon is the closest kind of a prediction can be possible with radon.
Yeah. Okay. Okay. Thank you, Dr. Gopi. Maybe if there are some other questions, if you still have question, please ask the question, raise your hand.
So meanwhile, I would also say you can think, if you have a question, please also. Ah, great.
Yeah. Okay. So you receive any? You receive some question?
Yes, yes. I have put up a software that means a program that derives TEC from a Rhinex data. Any GNSS receiver, if you have, and then you want to process the TEC, one can use my application that will give the TEC right away.
Yeah.
And then also there are now people have been doing multi-parametric studies, like they have radon electric field mill, which measures the electric changes in the electric field at a surface level, and then changing the ion counter, using an ion counter at a surface level, how the ion counts, positive counts, and then space charge separation at a, means when we have an atmosphere at a surface level, there are still some ions being generated, though they have a smaller recombination rate, but still one can measure the positive ions and the negative ions. The difference in the counts of positive ions and negative ions is termed as a space charge. People are also studying space charge. And then doing these multiple studies and then removing their diurnal variation, maybe in future we should be able to get there.
Okay. But I think it is really interesting that you explained before that the Rayleigh wave velocity from the DEC is in great consistent with the
surface Rayleigh velocity on the ground
from the seismometer, right?
Yes.
Do you find this kind of fact in other location?
Yes, it should be. It is applicable everywhere. Because we used about 35 GPS receivers to do that, to do the Rayleigh wave velocity analysis, and then we found the velocity is matching. Of course, it's there is a one-to-one correlation. We will not say exactly to the decimal point, but it is matching.
Okay. Okay. So we have a big chance to obtain a good precursor for this earthquake, right? But the problem is mostly, I think, almost all of study are conducted after the earthquake, not before.
Yes.
So they try to find the similarity, or they try to find a consistency with the phenomena and try to derive some precursor after that. So this is the problem, I think. Okay, if there are some questions, so we still have time, maybe 1 or 2 minutes. Okay, Dr. Gopi, are you working in this topic now?
I am also working on this topic. I am working on two topics. One is ionospheric irregularities, how they expand, whether we can say what is the amount of region that is being affected because of an ionospheric irregularity. Trying to use machine learning for it. And then the second one is not the ionospheric precursors, but we are also trying to see if we see a signature in an ionosphere, and then we want to delineate, means we want to separate out that signature, like this signature is either because of the ionosphere or because of this or because of that. And we are also studying a couple of earthquakes to see whether different types of earthquakes have a different kind of signature, or if so, how they are related with the type of an earthquake. That kind of a study is also happening, but we would say
because I think long time ago you are working in the computation something, right?
Yes. I was working on 3-dimensional tomography of ionosphere at the time.
Yes.
Now, but in India, we do not have that many GPS receivers to do that 3-dimensional tomography. So I had to switch the field because I was also interested in doing that. But then our institute said, do something which is in our country. Because if I work on the Japanese data, that is also useful because you can apply it. But then that kind of 1,500 or 2,000 receivers we can never deploy in India.
Yes.
So we have to see some system which is useful for put together a couple of tens of receivers. How it will be useful for that.
Okay.
So now we are working in that direction.
I think we have a good chance to collaborate with you.
Sure.
Yeah, I think some of our staff are working in this topic now, and they can collaborate with you, and maybe they will send email to you.
Yes, they are welcome.
Okay, everybody, and Dr. Gopi, I think we are at the end of this lecture.
So,
maybe
sorry,
Dr. Gopi,
Mr. Marzuki, can you read the question from Mr. Afrizal in chat room?
In chat room?
Question from Mr. Afrizal.
Yes.
Maybe Dr. Gopi, could you?
Yes, I have seen. What do you think about using the ionosphere data for earthquake prediction? Is it possible? Yeah, I have already.
Yeah, answered. I think you already answered, right?
Yes.
Yeah.
Okay, sorry.
No problem.
Okay, thank you. Mr. Arif Budiman is our faculty member, and he's is now in Australia actually.
Okay, great. Thanks for
Yeah.
joining from there.
Nice to see you.
Yes, yes.
Okay, I think we are at the end of this lecture. It's very interesting. Maybe Dr. Gopi would like to close your lecture today before I close this lecture.
Okay. Okay, thank you everyone for your interest, and then thank you for your time. Okay, take care, be safe.
Okay, thank you
Okay,
again,
okay,
Dr.
Madhusudhan, thank
Gopi.
you. Bye bye.
Thank you very much for your interesting talk. For me, this is really interesting because you know that we are in the gold mine of the disaster. You know.
Yes, yes, yes.
Yeah, therefore this topic is really interesting, and we are conducting some research in this topic as well
Sure.
to try to reduce the impact of this disaster on our community actually. So again, thank you very much. I think
Thank you all. Thank you all.
we are going to
Yes.
contact you again in next time for maybe some research collaboration,
Sure.
maybe some of my students will ask you about something regarding the TC.
Sure, definitely. They are most welcome.
Thank you.
Okay. Okay, bye bye.
Bye.
Thank you.
Bye bye.
Gopi.
Thank you.
Bye. Thank you. Bye.
Okay, I have problem with my connection, and also thank you for all the participants of this lecture. Thank you for your active participation, and I hope you enjoy this lecture. I think we will have other lecture. I think we will have other lecture in I think next month in I think in climate, regarding the climate next time. So we are inform you. Again, thank you, Dr. Gopi.
Yeah,
See you
thank you.
next.
Thank you guys. Bye bye.
Be safe.
Bye.
Okay. Bye bye.
Bye. Nice to meet you.